So I'm working right now as a visiting assistant professor of hydrogeology at the University of Mary Washington. And that's just sort of one of the job titles you can get if you get a degree in soil and watershed science or soil science. Hydrogeology and hydrology is still going to be fairly accessible to you. And I'm going to talk to you today about oceanic pedology and sort of raise the question of, is there a depth too deep beyond which we should not really be thinking about pedological concepts? And really, it's the realm of oceanographers and geologists and maybe others. Or perhaps there is not a lower depth. Maybe there really is a place for pedology, no matter how far deep you go into the ocean. And we're going to sort of take a look at that and address it. So when thinking about the boundaries of pedology and kind of how far we can push it, we really have to think about what soil is, right? Because if you're asking where does pedology apply, then is soil there is kind of an important question, because if it's not, maybe pedology is not such a useful concept, because that's the study of soil. Now, this is kind of a pedology course, right? And so I'm sure you've seen these first two sort of models that we use to think about soil formation and what soils are. There's the factors model, Hans-Jenny's model, and that is that soil is something that you get as a result of the interaction of all these different factors of soil formation. Usually it's conveyed as 5: climate, organisms, relief or topography, parent materials, and time. Some people have tried to rewrite that and apply that a little differently in the subaqueous environment, but I think it works just fine. You don't really need to include different factors for water depth or water chemistry, because they're embedded in those factors. When you talk about relief or topography, that is bathymetry, that is water depth, that is your flow regime. That's all controlled by your topography, by the shape of the bottom. And so that's already captured in that. When you talk about parent materials and climate, well, that's something that's sort of reflective of water column characteristics, right? Where you are in the world is going to determine the salinity of your water and the chemistry there. And that's going to have an influence on the sediments underlying that, the types of ecosystems that you get in those aquatic environments. So I would say that the factors model sort of fits conceptually reasonably well these circumstances. And then there's the processes model. And that is that soil is something that you get as an interaction of 4 fundamental processes: the additions of material, losses of material, transformations of material, and translocations of a material through a profile. And that's most materials at Earth's surface, right? Anything you've got, any spot on Earth is going to have stuff occasionally being added to it, either because sediment's coming in or plants are putting organic material down, or deposition is happening underwater or under the atmosphere in terms of dry deposition. Losses, you're going to have erosion and leaching and decomposition, releasing things into the gas phase. Transformations, you're always going to have decomposition, turning some kinds of organic matter into other kinds of organic matter. You're liable to have mineral transformations from one kind into another kind, depending on your environmental conditions. Redox is a big one there. Certainly wet environments have a lot of transformations going on. And translocations, materials moving up and down through the profile. Anywhere you've got bioturbation, for sure, you've got that going on. And so those are the sort of 2 general models that we use to think about what soil is. But if you're a definition person, there's an endless list. There have been many review papers written on definitions of soil. And you can find dozens of pages of definitions that have changed through the years. The latest one, the one you see on this slide, this is one that's recently been adopted by the Soil Science Society of America. And so this is a pretty high authority on what soils are. Says that soil is the layer or layers of generally loose mineral and or organic material that are affected by physical, chemical, and or biological processes at or near the planetary surface. That's a key term there, planetary surface, and usually hold liquids, gases, and biota and support plants. Well, what's a little notable about this compared to some of the earlier definitions and earlier concepts of soil as just kind of a medium of plant growth, or soil as the living skin of the earth? Well, this definition says planetary surface. And so this is an effort to include extraterrestrial soils and regoliths, materials on other worlds in the solar system, and probably other solar systems as well, within the definition of soils. And that little caveat there, usually hold liquids, gases, and biota. allows that sort of abiotic material to be included as well, the regolith, the lifeless stuff that we find on the moon, or presumably lifeless. That's very controversial right now, and there's a lot of discussion about that and debate in that whole realm of astropedology, which is kind of the next frontier that I'm not going to really talk much more about today, but just to, you know, illustrate that the soils concept is one that's evolving and that people don't always agree on, and it's almost as complicated, if not just as complicated, as asking a biologist what life is, or a physicist what matter is, right? These are the deep questions that kind of underline some of our scientific disciplines. And then, of course, the practical side of things in U.S. Soil Taxonomy, Chapter 1, that's the chapter of the soils that we classify. They have a giant definition. Essentially, it's a page and a half, because they don't have a simple definition for soils. They just talk extensively about situations where soil taxonomy applies. And that does allow, since the second edition, subaqueous soils to a depth of about 2.5 meters of water. And so if you've got less than about 2.5 meters of water, soil taxonomy says you can have subaqueous soils. And just so that you know a unit that's going to come up a few more times in this talk, that 2.5 meters is about equivalent to 1.4 fathoms. 1 fathom is 6 feet. And if you look at bathymetric charts and you start working in subaqueous soils, you're going to have to know what a fathom is. It comes up all the time, especially in the United States, because we've got these crazy old units, right? Fathoms and feet and things. So if you look at old charts and stuff, you're going to see a lot of fathoms plotted, and it's just a sort of a fun unit to work with. And so up until the 1960s, all those sort of concepts of soil, the early concepts, certainly not the new SSSA definition, carried soil survey up to that yellow line, more or less. All those farmlands, all the forests that you see there, those were the things that were surveyed and given taxonomic names, and soil series were developed for them. And that's because those were the soils that were useful, right? That's what people were using up until the 1960s very heavily, and they needed a lot of information about these materials for tax purposes as to which land got taxed at a higher rate because it was better agricultural farmland. And so this ties into tax values and property values and so forth. And you notice on the right side of that line, we've got some TM and W letters. Well, those are map units that were just drawn in for areas that weren't as useful. And so in the soil survey, up to the 60s, all that stuff up to that yellow line would be broken up into many very detailed map units with all kinds of soil information provided on each one. And then the marshes were usually just mapped as TM, tidal marsh, but that wasn't always consistent. Sometimes you'll see SM for soft marsh, and HM or FM or something like that for hard marsh or firm marsh. And so it was irregular. It was just sort of ad hoc. Whatever the surveyor wanted to call the marsh, they would sort of jot down. There wasn't even a clear set of rules for it. And then the water bodies were just water. Absolutely no information was provided about any sort of sediment or soil under any body of water. Similarly, beaches, just called beaches, and all sorts of other miscellaneous areas weren't handled very well. But pedology has kind of marched along slowly since then, but consistently, from those agricultural applications and surveys, which were suitable and reasonable when they were made, right? In the 1960s, people didn't quite understand the importance of aquatic and coastal environments. Ecology was just sort of coming into being as a discipline in itself. And so environmental issues weren't really at the forefront of what a lot of soil scientists were thinking about at the time. But since then, of course, soil science has moved from ag and range and forest land into wetlands, and now shallow freshwater and even marine environments. And it's been advanced by pedologists over the years. And if you go through the literature and want to read some great landmark papers, look for papers by people like George Demas and Marty Ravenhorst. Marty was my advisor. And Mark Stolt, who's presently at Rhode Island. And a lot of other people who've worked on this. But you can read all the papers on subaqueous soils, I would say, in a semester. If you really put your mind to it, there's probably not more than about 30 or so right now. It's a kind of a small discipline, but it is starting to take off, and the surveys are rolling in. And now, yes, since the second edition of Soil Taxonomy has come out, we're also mapping and talking about Antarctic soils. And so some caveats have been made in the definition for that. And like I mentioned previously, astropedology. There's no lunar soil survey yet, but who knows, 20 years from now, 30 or 50 years from now, what might develop. And so from the 1970s to the 1990s, there was a recognition of the importance of hydric soils and wetlands for a whole variety of purposes. I would say one of the key ones in coastal states is water quality protection, right? These environments can be sources or sinks of nutrients. They can be regulators or destroyers of water quality, depending on how they're managed. And so it was important to provide information about these environments. And now we're learning that these coastal environments are extremely important for climate regulation as well, because even though they may just be a little fringe between the dry and the wet parts of our environment, there where a great deal of the carbon is stored, right? You might have 3 or 4% organic carbon in an A-horizon agricultural soil. You might have 40 or 60% organic matter in a histosol, one of these coastal tidal marsh soils. And so there's a lot of carbon tied up in these, a lot potentially to be released, and a lot of space where additional carbon can be captured and stored. So from the 70s to the 90s, soil survey really started to provide more information on wetlands, more useful information. And now there's actually a proposal to create a whole soil order in U.S. soil taxonomy for wet soils. We've got the 12 soil orders, and right now wet soils are found in 11 of them, I think, just not the aridosols, which are by definition arid, dry soils. But I believe all the others have wet soils in them, and there's a recognition that that's important enough for our management concerns now that maybe those soils should be their own order altogether, and we should really be thinking of them as wet soils rather than wet versions of the 11 other soil orders. And then from the 1990s to the present, especially with the work of George Dimas, who kicked this off in the late 90s, we've had an expansion into the subaqueous environment. And so the legend goes that George was a soil surveyor in Maryland, and he was digging holes in a tidal marsh here, as we see up to the green line, and got to the edge and looked into the water. And he had just been taking these cores and he's mapping this landscape, and he looks down into the shallow water just off the edge, and he sees submerged grasses and crabs crawling around and fish. He sees this biodiverse, excuse me, plant-rich environment just teeming with life. And he says, well, why stop here? You know, why do we stop right at this edge and say the soil's concept extends no further? There's plants down there. There's all this biodiversity. There's all this function. And so he did the work to show that underwater, at least in shallow environments, you do in fact have distributions of these materials according to those sorts of models of soil formation. And he's the one whose papers got that change made in the second edition of Soil Taxonomy, allowing for subaqueous soils to about 2.5 meters water depth. And so you can make a big change if you're out there asking a question, right? And you write a couple of papers, you might not realize it, but you can easily have a huge influence on some niche scientific topic like soil taxonomy with what may seem like a relatively small question if you put your mind to it and work at it. So my work was on Road River. That's what you see here on the right side. This is the soil survey that I produced for Road River, which is one of the sub-estuaries of Chesapeake Bay. Chesapeake Bay is the biggest estuary in the United States. It's got a number of these smaller branches on it that are much easier to map. I couldn't have tackled the whole bay. It's going to take some years for that to get mapped. But one by one, we're knocking these little sub-estuaries out of the way. I've been involved in 3 of these now. 4, I think, actually. 1 on the other side of the bay as well. Road River extends to a depth of about 4.5 meters. That's about 2.5 fathoms for those of you who've been paying attention to the fathom units. Now notice that that's a little deeper, right? And so even just in this one little small branch of Chesapeake Bay, just this survey trying to constrain it, we go 2 meters beyond that 2.5 meter depth, right? Blew right past it in terms of generating this map. And so I got some challenges and questions about this by people who really wanted to stick to that 2.5 meter depth. But I couldn't find any straight line. I mean, there's not an edge in the environment at 2.5 meters. That was just an arbitrary number that some USDA people sort of settled on via consensus that's in the current version of soil taxonomy. It's not sort of biblical truth or anything like that, right? It's just an ad hoc number. It doesn't necessarily represent some concrete physical change, less than 2.5 meters, you've got soil, deeper, suddenly it's sediment. No, it's the same material on either side of that boundary, and it's very similar to a much deeper depth as well. And as you get deeper, properties change slowly to different types of materials. There aren't a lot of bright lines in nature that let us easily divide things into different categories. Sometimes we've got to sort of deal with fuzzy boundaries and things like this that slowly change over gradients. And so Road River has a lot of submerged uplands and recent sediments, and that's one of the things that complicates it, because in areas that are deeper than 2.5 meters, you'll find upland soil that's just been down there for a few thousand years, submerged by sea level rise, right? And it was left intact. It used to be an upland environment 10,000 years ago when there were a bunch of glaciers on North America and sea levels were lower. The whole of Chesapeake Bay used to be a great big valley. And then when those glaciers melted and all that water went into the ocean and sea levels came up over the past few thousand years, it flooded Chesapeake Bay. And so these not just are soils today, I contend, but were certainly soils in the past. And when you dig holes in them, you find those old subsoils. And you see on the left side of this image, that reddish brown subsoil. That's an oxidized soil that existed for a long time, thousands of years ago, subaerially, right? It accumulated those iron oxide colors in there down below about 80 centimeters, you see in that picture on the left. And then it was submerged and has been preserved and altered and changed in some ways since submergence. And so we've got ongoing pedogenesis, ongoing changes in this material due to additions, losses, transfers, and transformations of minerals leaching in and out of this, and organic material coming and going, and now marine worms instead of terrestrial worms, and instead of the regular roots, we've got roots on submerged aquatic plants that are in some of these materials. And so it's very analogous to what we think of as upland soils. Now, this ties us into an important concept or set of concepts. There's early diagenesis, and pedogenesis. And these get thrown around a lot in different disciplines. Diagenesis is a sort of geologic concept. It means second genesis. And it's kind of the process of physical and chemical alteration of sediments. Big picture. Most geologists would exclude surface weathering, and so that's kind of how they try to carve pedogenesis out, and metamorphism, and so metamorphic rocks are their own thing. And some people may or may not say that diagenesis passes lithification, right? So some people would say that you set sediments down, and if they're altered in some way, that's diagenesis. But as soon as they turn into rock, then it's metamorphism or some kind of geologic process. But again, it's fuzzy boundaries, right? These are just things that occur in nature that we've tried to put into boxes, and they don't fit very well into those conceptual boxes. Early diagenesis, though, is a more simply defined thing. Early diagenesis is a concept that's used more exclusively by people who study recent sediments, aquatic sediments, usually marine, and they're just looking at the biogeochemical zonation and alteration of those recent sediments controlled by the material type and the biological, chemical, and physical alterations going on there. And so that is exactly, I would say, the same thing as pedogenesis. You're just looking at the alterations in the upper part of relatively recently deposited materials. That's pedogenesis. It's also early diagenesis, and it's a subset of diagenesis as the larger concept. And you can see the table here. We've got sort of the generalized processes of soil formations, additions, losses, transfers, and transformations, and then some corresponding sediment diagenetic or early diagenetic processes, right? And so we just talk about additions. Really, that's inputs of minerals and inputs of organic debris is how the marine scientists think about that. Well, those are the same thing, right? It's just slightly different ways of saying the same thing. My point here is that soil scientists and the marine scientists who study these benthic environments are studying many times the same thing in about the same way with about the same language. It's just important to understand that you need to learn a little bit of each of those foreign languages if you're going to work in this kind of multidisciplinary or transdisciplinary field. What you see in that image there, these are Pyrite Framboids that I extracted from a recent marine mud. And this is just an example of something that forms as a result of both early diagenesis and pedogenesis. You could say these are a pedogenic feature of these soils because these tiny little spheres of pyrite form. They're precipitated out in these reducing environments in these marine muds. They just form as little beads, and they are the coarsest material in these fine muds. And when you separate them out and do a density fractionation, it turns out they're almost 100% of the heavy mineral grains, just this precipitated pyrite as a result of early diagenesis, also simultaneously as a result of pedogenesis. No real difference there as far as I'm concerned. So where's this going, right? That's all kind of just constrained to the first couple of meters of depth. And we've got the Coastal Zone Soil Survey now where the NRCS has decided they're going to go out and they're going to map subaqueous soils along the coasts of the United States. But all of that is constrained not only to the continental shelf, but really just to the tiniest, shallowest corner of the sea on this diagram, right? The continental shelf extends to several hundred meters water depth, much deeper than the 2.5 meters, right, that the NRCS is usually looking at. And then, of course, the deepest zones in the sea go down to something like 11,000 meters. And so there's this abyssal plain that covers more than 50% of the Earth, and that is between 4,000 and 6,000 meters in water depth. The materials do vary widely across all of this, from the continental shelf all the way down to that ocean trench. And they're not very well explored, right? And so I think it's premature when people say there aren't soils down there, because consider the Challenger Deep. The Challenger Deep is the deepest known point on Earth. It's one of these deep trenches way down in what's called the Hadal Zone, about 11,000 meters down, and it's only been visited by 13 people, 13 explorers in the history of the world. That's one more than the number of people who have walked on the moon. 12 people have walked on the moon, right? And so we do not have a very good understanding of this environment. We have not explored it extensively. We've taken a couple of peeks, right? Barely more than we've looked at the surface of the moon even. And in the case of the Hadal Zone, that deepest portion only covers less than about 0.25% of the seafloor. Those trenches are really a small portion of it. Most of it is the abyssal plain and is not quite that deep, but is similarly underexplored in a lot of ways. So let me take you in the time we've got left on sort of a cruise out into the open ocean, into ever deeper water, and show you and talk about some of these things. So we'll start with the continental shelf. This is the most reasonable, right? If you can map soils in 2 meters of water, then as that gentle slope continues all the way out to the depth of a few hundred meters before it starts to drop off precipitously at the edge of the continent, then that's kind of similar material, right? You've got bands of sand running up there. You've got a lot of shellfish. That's where a lot of clams and oysters grow. That's where, great sorts of herds of lobsters move back and forth across the continental shelf. And so there are lots of really important ecological interpretations to be developed and fisheries to be managed out there. The average depth of the continental shelf is about 60 meters. Now, of course, that varies a lot. That's about 33 fathoms for those nautical types who are paying attention to those units. During the Pleistocene, remember that last glaciation, all the glaciers are holding the water on the continents. Sea levels were about 130 meters lower than they are today. And so these shelves all along the world were exposed. And think about it, like another Louisiana worth of Louisiana, right, on currently the seaside of your coast would have been exposed. A massive amount of land, and there are forests and bogs and upland environments and topsoils with roots in them that have been submerged and shallowly buried and preserved under all that water. And way out there on the continental shelf, many of those landscapes are still at least partially intact. You see the image on the right side here. Those points are locations where large skeletons have been pulled up from mastodons and mammoths and walruses and ground sloths, right? The Pleistocene creatures that lived there, not because their bones have been transported and were found in loose sediment, but because that's where they died and were fossilized. And during dredging operations, sometimes we hit those deposits and we pull those things up and we can see, oh, wow, there was a great forest here and it was occupied by a bunch of mastodons 10 or 15,000 years ago. And so I would say that those were soils at the time, and that at the very least, many of those soil properties have persisted to today, and we can still see them. Moving sort of beyond the continental slope, which is very steep and has turbidity currents, into the abyss, where I think is a lot of interesting materials to be found. The abyssal clays are about 70% or more clay. And so that's because once you get into this really deep water, 4,000 meters deep or so, and you're so far from the coasts of the continents, nothing else gets out there. All of the sand and silt settles out before it gets into that deep water because of the energy of the water, right? You don't have enough moving water deep down in the water column to transport large particles. And so the only thing that gets brought out there are the tiniest clay particles that very slowly settle out. The sedimentation rate in the areas where these clays are is between 1 and 5 millimeters per 1,000 years. Incredibly slow sedimentation rate. And one of the surprising things is that one of the minerals that's most common out here is hematite and iron oxide, a very highly oxidized iron oxide that you really certainly would not expect to find in reducing conditions. And we'll see more about that in a second. But those abyssal clays, those hematite-rich clays cover perhaps 38% of the ocean floor. And so these materials are all over the place, and their chemical and physical properties vary with depth. I've included a picture and a data chart here just from an example one. You can pull these from various coring projects that have been conducted and look at the profiles, and you can see this one has some carbonate changes with depth. So it's not just uniform material. The reason that you find hematite out there is because some of these areas are highly oxidizing environments, even to a depth of dozens of meters below the seafloor, right? How do you get oxygen dozens of meters into a fine textured, clayey, muddy seafloor? You would think that would be a reducing environment. You would expect to find a wetland soil, right? A hydric soil type thing. It turns out that in the open ocean, the supply of carbon is so low in some areas that biological processes are arrested. They're going at a very slow rate in these sediments, and oxygen is able to work in via diffusion and make it 80 meters into that material because there just isn't enough carbon to be decomposed to create that biological oxygen demand. So that's a very interesting thing about the seafloor that sort of sets it apart from the other wet soils we think about. Very interesting material. A lot of the rest of it is made of oozes. So you've got the abyssal clays, but you also have calcareous and siliceous oozes. And these are the tests or the skeletons of different types of microbial organisms. Some of them are silica, some of them are calcium carbonate. And there are these compensation depths. And so below about 6,000 meters, for instance, you won't find opal because it dissolves. Below about 4,200 or 4,500 meters, you don't really find calcite because it dissolves, just because of physical chemistry processes. The pressure increases, the water chemistry changes, and that just determines the distribution of materials. Well, that sounds like there are factors controlling the distribution of these materials, right? If you have an ocean surface that's warm, then you're going to have calcite secreting organisms. And if it's cold, you're going to have silica secreting organisms. And that's going to determine what kinds of materials you find on the bottom. And if it's shallow ocean, like you find at the mid-ocean ridge, where those seafloor spreading ridges rise up towards the surface, then you're going to have carbonates near the surface. But as you move away from that and you get into deeper water, those carbonates will be blanketed by, in warm water, calcite, and cool water, silica, and preserved. And so then you start to get sequences, right? You get layers, you get horizons developed based on where you are in the world, based on the climate and the relief and the organisms that are acting on this to create different types of parent materials that change through time, right? How could that not be soils? Pedology applies perfectly well to this environment. And so now with the last couple of minutes, and feel free to cut me off if I'm going on too much. I think we're getting close-ish to the target. I'm going to talk about some interpretations and useful things that we find, oddball things that we find in these landscapes. One of them are manganese nodules. This is no longer a fringe topic. This used to be sort of something that crazy people talked about because there were these manganese nodules, baseball sized, softball sized at the bottom of the sea, but they were so expensive to go after that nobody could ever mine them with any sort of profit in mind. They're really rich in metals like manganese, iron, nickel, zinc, copper, cobalt, and molybdenum, just to name a few. And they vary in composition based on their distribution, and their distribution varies based on other factors. You see on the right side of this slide, sort of looks like a soil map, right? Looks like soil map units. This is the Clarion Clipperton zone where they've tried to identify the zones of highest concentration of these nodules worth mining. They form at the sediment surface. They stay there for some reason. We're not quite sure exactly how, but we don't find whole columns full of these. And so as the sediment accretes, they tend to make their way up in the profile. They stay at the top. They can be thousands or millions of years old. They form very slowly. They are associated with certain regions and landforms, and we do have an idea that there's topographic or pedogenic controls over where they are. So they may be sort of something we can think of as a soil product. And right now, the initial studies are going on in the Pacific. They're getting baseline data because there is about to be a gold rush. The technology is there and the economics are there now for this mining to begin, and it's starting. And countries are getting leases, and this is happening, and there's going to be a lot of environmental damage as a result of it. So we need to learn how to minimize that damage, how to make up for it where we can, how to do this responsibly. I think soil scientists have something to say about that. Similar to that are ferromanganese crusts. These are like the nodules. They tend to be richer in cobalt, again, a valuable material. These tend to form on hard rock seamounts. They can be up to 2 meters thick. So 2 meters of sort of solid ferromanganese material rich in cobalt. It is solid, it is rock, but we do describe pedogenic rock, right? We talk about durapans and petrocalcic horizons. Just because something is rock hard doesn't mean it can't be a part of a soil profile. Quite the contrary, if it forms at the surface as a result of pedogenesis, we would certainly say it's a pedogenic feature. And I would say there's a case to be made that these ferromanganese crusts are pedogenic features. Then there are massive sulfides. These are the ones you find at hydrothermal vents and black smokers. They can be active or inactive depending on whether they're currently volcanic. The temperatures at these can be colossal, 464 degrees Celsius, well above boiling, but kept from boiling by the pressure, very high pressure at the bottom of the sea. Unlike the nodules, these ones tend to be richer in gold and silver and lead, different metals, some of which are also extremely valuable. And also associated with these are totally unique ecosystems, right? These are biodiversity hotspots in the deep ocean. There are not many of these sulfide deposits, and they're only really scattered along the mid-ocean ridges. So very delicate environments, maybe ones to be protected. And then sulfide and heavy metal enrichment in sort of metalliferous muds. So this is a seamount out on the west coast. This is one that's erupted into the sea a few times. The surrounding sediments are really enriched with sulfides and volcanic glasses and different kinds of metals. And that material is distributed, right, according to the topography and the other factors that form the materials here. And we can make realistic maps of that provide meaningful information. And now that we're entering an industrial age at the deep sea environment, it may be time for that information to be provided. There are cold seeps as well, just sort of one last thing I think here. They're not really cold, but they're colder than the hot vents, which is why they're called cold seeps. But these are where other sort of warm hydrocarbon-rich fluid seeps into the ocean. There can be a lot of hydrate deposits, very unusual minerals with sort of organic stuff in them we don't usually think of as minerals, and strange concentrations of salty brine that stays separate from the rest of the seawater thanks to its density, as sort of brine pools sitting liquid under the liquid ocean. And so what do pedologists have to contribute to all this? I would say that in my time working with marine and aquatic scientists, we know a lot more about mineralogy. Soil scientists come to the table with a lot of knowledge about clay mineralogy and reduced minerals and things of that sort, and contribute that. We know a lot about exchange processes. You read almost nothing about cation exchange in the marine literature. It's sort of assumed to be negligible. I think that's not always a safe assumption. We know a lot about classification and survey. We have a lot of experience classifying materials. U.S. soil taxonomy is not perfect, but it is the best, I would say, soil taxonomic system in the world in terms of how thoroughly developed it is. Not to criticize any of the others, WRB is also a great system, but taxonomy is very well thought out. It's got a lot of work that's put into it, and it can accommodate these marine materials with new classes that can be developed, right? The process, the system is there. We have land use interpretations, and so we have a very applied mindset a lot of the time. We're thinking about shellfish. We're thinking about how to set up a harvest regime where you could maybe collect those manganese nodules and set up the conditions such that they would form again, right? Imagine farming the seafloor for these things. And of course, we have legislative backing. The Federal Geographic Data Committee of the U.S. government has in one of its publications, CMEX, the Coastal Marine Ecological Classification Standard, the statement that it is recommended that a soils approach be used if a more detailed classification is needed for interpretations and management of shallow water substrate. That is a major sentence, right? It doesn't look like much, but this citation has been used to justify and build the case for a lot of coastal pedologic work, because when you're dealing with the government, you need these types of documents and these types of citations to say, yes, this is an authorized kind of federal activity. Thinking ahead to the future of pedology, will future pedologists sit around discussing abyssols? I think it's plausible, right? The abyss all the way down there, 4,000 to 6,000 meters deep. Again, for the nautical types, about 2,200 to 3,300 fathoms. That does admittedly exceed the recommended maximum depth of about 2.5 meters or 1.4 fathoms. But I don't think that that depth alone, that the fathoms alone, make oceanic pedology unfathomable.